Hi everyone, welcome to Beginners Python and Machine Learning. This is the first time I've done a YouTube live, so bear with me. Can you hear me okay? Try responding on Slack or the chat. Thanks, Helena. All right, now I've sent out a URL on Slack, and I've also put it in the comments on this YouTube live video, which will be a copy of the Jupyter notebook that we're going to work through. So people could try getting a copy of that. Use the URL, you can see it in view only mode, and so you'll then have to do a copy for yourself. So let me know in the comments, in the chat, or in Slack if you've got that working. It looks like I've got 7 concurrent viewers at the moment. So this is the URL that I'm expecting you to use to get a copy of the notebook. I've got 8 concurrent viewers. Welcome, who've just joined us. So we're currently setting up Jupyter Notebook. I'm going to use collab.research.google, so you can get a copy of the notebook that I'm going to be using from this address. If you've got the one from last week, that'll mostly be the same. There's a couple of changes. All right, let me know if you need more time to get that notebook, but otherwise I'll start working through. So I think this is a continuation of what we did on the 25th of February, and we covered quite a lot of stuff then, so I'll probably spend a fair bit of time reviewing what we went over last time, and then we can start getting onto the actual optimization side of things. But there's a fair bit of setup in getting it ready to optimize. I'm going to assume you're familiar with how to use Jupyter Notebooks, but certainly ask questions in the chat or Slack if you are not. Vince says there's noise in the background. Is it like fan noise? Because my fans are going. So okay, so tonight we're going to use these libraries, pandas and scipy.optimise, and we'll also use we'll probably be using matplotlib as well. So we'll import these libraries. So if I select this cell and I press Shift Return, it's imported all those libraries. We want the plots to show inline, so we'll run the %matplotlib inline. Now, I've been using pandas in this session, and it's the version of pandas and version of matplotlib that Google Colab are currently using. I've currently thrown some errors, some warnings. So I'm just putting this cell in here to turn those warnings off. So I'll run that and they'll filter out those warnings. These are some functions that I've defined for plotting the graphs. We don't need to go into the scope of these during this session, but you will need to execute this cell so that it defines all those functions, so we can call them later to plot our results. So I'll just press Shift Enter on that, and that will define all those functions. It won't do anything other than define the functions. Right, now going back to February, our first challenge was to read in the electricity production in megawatts from a solar farm for the month and find the average for each hour of the day, plotting the results. And we're going to use the Emerald Solar Farm data. We're going to get the data from this website here, which is nemlog.com.au, and you can explore on there. I generally look in mlog, and he's got a whole bunch of different filters that he's put on, and with those filters you can see how he's done it and then get an idea. So for example, Queensland large-scale solar will show some of the solar farms that are currently in Queensland, and there's the Emerald Solar Farm, is EMERASF. So the form of the URL will be something like this. We're using his API that he's set up, and we're looking at a particular unit, which is Emerald SF1, and this is a start date, and this is a finish date, and his API, we just say /CSV, means we'll get the file in a CSV format. Now the plan is to download this file once and then use it from then, because it takes a bit of time to get it from his site every time. So I've done it once, but we can start off without having the file here, and I'll show you how we do that. So if we try to read the file that doesn't exist, like this, so we have the file name, unit Emerald SF1, this is just a name we've made up, and we want to read it into a data frame using pandas. If we execute that, we'll get an error, and the error we'll get is file not found error. So basically we want to read it from the file if the file exists, but if the file doesn't exist, then we'll go off to the web and we'll download it from the web. So what we can do, those two lines that we had file name, we defined the file name, and then we read it. We had the error happen on the read CSV, so we can surround it with a try except, which means that if we do get a file not found error, then we'll go to the web. In this case, we'll use the URL that we've got here, and we'll read the file, read the CSV from the URL. And then for the future, we'll just save that data frame to a CSV. So in the future, we can we won't need to go back to the URL. So we're creating our own cache. So let's run this and let's have a look at what's in the data frame that we get from it. You can see it's taking a little bit of time to go to the Nimlog site and get the data. And this is what the data frame looks like. It gives us a settlement date as the index. And you can see that's showing every 5 minutes what the data is. So 5 minutes after midnight at Emerald Solar Farm 1, the electricity price is $50.8115 per megawatt hour, and the SCADA value is 0, which means we're getting 0 megawatts from that solar farm. It's at the middle of the night, that's what you'd expect. And so this isn't actually very interesting data at all. So let's see if we actually got some interesting data. So we'll just put a filter on that and see if there's any values that are greater than 0. Now I'm going to run this whole cell again, and hopefully it should be faster because the file should now exist. If I look in here, the file now exists. That's good. So I'll run this with Shift-Enter. And here we can see at 6:05, that's when the solar farm started to produce some output. And it was 6 megawatts, 6.27 megawatts. And then 5 minutes later, it started to build up to 10.67 megawatts, 12.83. And that kept going, it's on the 1st of January, all the way up to the 31st of January at about 6:55 p.m. And it was finally only producing 0.48 megawatts, and then it was just 0 after that. And so obviously every night between the 1st and the 31st, it would have been 0 as well. So that's good. We're pretty confident now. We've got in our data frame the data that we want to use. So next thing we want, we're going to plot by hour. So we create a new column in our data frame called hour, and it's just going to be, it's going to take the settlement date, which is a date time object, because we told it that, and find the hour for it. So once we've got that extra hour column, we can group by the hour, and the data we're interested in really is the RRP and the SCADA value, and we want the mean values for that, and then we're going to plot them. So this is a review of what we did in February, so I'm going over fairly quickly, but if you want me to slow down on any part of it, just let me know. Okay, so this is the data. You can see that for any of the days between 0 and 5 a.m, we didn't get any solar production at all, but after 5 a.m. we started to get, and this is the average of all the days, say at 5 a.m, this is what the average of all the days at 6 a.m, 7 a.m, 8, 9, 10, down to about 7 o'clock at night. And you can see the price of electricity in Queensland averaged over the days, so it has quite a lot of spikes in it, but if we just take an average, it's averaging about $50 per megawatt hour in the mornings, and then in the afternoon the demand increases and the average gets up to about $140 per megawatt hour at about 7 p.m, 6 p.m, and then later at night it drops back down to $50 per megawatt hour. So we got scope here with a battery. We can buy electricity at the cheap times, so we can sell it at the expensive times, and we've got a potential to make a profit out of that. Okay, so back in February we ran a demo with the car analogy. So we had a car that was driving along, and every time it came to a petrol station, it would look at the price and decide, is it going to fill up or not, just purely based on the price. Is the price too high, too low? It didn't look at what the level in the tank was. And if it was low enough, it would buy. If it wasn't, it wouldn't, and it ran the risk of running empty. If it did run empty, then it would have to buy, get petrol delivered to it. We had a price of that of $50 to deliver 10 litres of fuel. So I won't go into this one so much of how to create the object, because I'll concentrate on what we did for the battery. But we do need to run this so that I can do the demo later. So I'll just run this cell. That's created that's defined the car class. So now we can create objects of type car, and we'll plot the price for the day just to see what it looks like. So this is the day number as we're going along, and the price of fuel is changing from $1.75 down to $1.25, and then quickly spiking back up to $1.75 every 30 days or so. So what we did, we created a data frame which had some data in it. So let's look at this data frame that we created. It stores how many kilometres to the next fuel, and what the price is we saw then, and we're going to make decisions about whether to buy or sell at that time. And this is the total kilometres that have been travelled. Okay, I've just had a question from Howard about what the semicolon is in Python. So if we look at the semicolon here, the semicolon tells us not to, sorry for that bang, the semicolon tells us not to output the what comes from that line. So if I get rid of the semicolon and run it, okay, for this case it didn't actually do anything, but often we'll get a line saying what got returned. So I'll just create a new cell above. So let's see, we'll have, so if I just say df, it returns the df. If I say df semicolon, it means I want to just do df, but I don't want it to show the output in the Jupyter Notebook. So for plot price today, I want it to plot the inline thing here, but I don't want whatever gets returned by plot price today function to get shown here. We'll probably find there's nothing actually returned from plot price today, so I don't actually need the semicolon in that case. Okay. So racing through the car example, we defined a function here, cost for car fuel, given a price break. So this will summarize, if we choose a value for our price break of, say, well, whatever gets passed to this function, then we'll create a car using that price break. We'll run through all the rows in the data frame, work out how many litres have been purchased, and we'll also store what the current level of fuel is for the car at that row in the data frame. And we're just doing this on a row-by-row basis in the data frame. And then at the end of that, we can see what the total cost of buying fuel was to fill the car. So let's define this function, and I'll press Shift Enter. and the now I'll run the function with a price break of $1.40, which means if the price is cheaper than $1.40 we'll buy, and if it's more expensive we won't. Then we'll look at what we get in our data frame of demo, and then we'll plot the results. So we can see here in our data frame, as we're going along, the price is too high, we're not buying anything, not buying anything. Here's an example where we do, the price was $1.27, so we'll buy 7.14 litres, and that would be just to fill the tank. And the level would go up, but then after that, the price has gone up and we didn't buy any more. So we can see the orange here is the price going up and down, the blue is the level in our tank whenever we measure it, and you can see it's coming down here to zero quite a few times. So we've got a cost to fill the car of $1,148.76, and that'll include quite a few times when we've had to get petrol delivered to us. So if you run this in your own Jupyter notebook, you'll get a different answer because these are based on random numbers, but I'd be interested to see what values you're getting for this cost for your car. So send them in the chat or in the Slack. Okay, I've got Leo who's saying the results is currently a bit pixelated. So if other people are seeing it pixelated problems, let me know. I'm not sure what I can do about it. But, have a look. Oh, I think the chart is not showing. There's a chart. Let me know if it looks like I'm pointing to things off the bottom of the screen, because I may not have that screen set up properly. Thanks, Peter. Peter says his video is fine. So, Leo, it could be if you're not getting a good connection to the internet, then YouTube is pixelating it for you. Okay, and another Leo is saying try the settings code to see if you can select HD. I should be broadcasting this at 720p. Okay, did anyone calculate the cost to fill their car? Okay, I've got Peter's 1184, Elena's 1301. So it's not a tank, Peter. It's the cost over the month over the 100 times you filled up actually. So 100 petrol stations as you're driving along. It's set up for passing 100 petrol stations. So sometimes you don't stop, sometimes you do. And you can see the total number of kilometres travelled over that time. For me, it's 11,113, but for you it could be even a bit higher or lower because they are random numbers. Okay, and I presume everyone got some times on the graph that shows that the tank was empty on a few times. So just put that in the back of your mind, and we'll come back to how we can optimise that price decision to work out how to improve when we fill up our tank and maybe reduce the price of our fuel. So now we're looking at the challenge 2 that we looked at back in February. We want to install a Tesla battery like the one installed in South Australia to smooth the electricity output from renewable energy sources. So the specs on the Tesla battery, it had a storage capacity of 129 megawatt hours, and the power limit from or to the grid was 100 megawatts as the maximum rate you could put energy into the battery from the grid or take it out of the battery to the grid. It had a 90% efficiency, so if you took 100 megawatts to the battery for 1 hour, it increased the storage level by 90 megawatts. So our challenge was to create a battery class and to model the behaviour of the battery. So this is what we did. So similar to what we were doing with the car, we created a class. We only put two methods in the class. One was an initialization method. So when we create an object, an instance of that class, then it automatically calls the init method, where it's got double underscore init double underscore, and then there's the parameters that we provided. So there's some characteristics of this battery that are never going to change, but we need to know what they are for how the battery's going to behave. So it's megawatt hours capacity. It's how much we can put in. So it's generally going to be 129 megawatt hours for a Tesla battery. The limit of how quickly we can take electricity from the grid or return it to the grid is going to be stored in megawatts limit. The efficiency of the battery, which was 0.9, we'll store in a variable called efficiency. And then this battery object it represents a battery operator combination, because things like RRP brake, that's not actually a characteristic of the battery, it's a characteristic of the person who's running the battery. And so what we're saying is the RRP brake, we're going to store the way his logic thinks, which is that he's going to buy when the price is below the brake price, and he's going to sell when it's above. We're going to store, we're going to keep track of the level of energy stored in the battery, so how many megawatt hours are currently stored in the battery, so that's a battery characteristic, and we're going to store how much profit the operator of the battery has made. So to start with, both of those values are going to be 0, and then as they'll change each time a transaction happens when electricity is bought or sold. Now this second function we're providing, the decision function, is basically encapsulating the logic that the operator uses for buying and selling. So it's pretty simple. He's just going to sell when it's above RRP brake and buy otherwise. But we have to make sure that we don't violate any of the constraints. So for example, we can't sell more than is stored in the battery. We can't buy more energy than will fit in the battery, and we can't buy or sell faster than our limit in megawatts. And we have to make sure that when we buy 1 megawatt hour, we only store 0.9 megawatt hours in the battery itself, because we've got to take into account that efficiency of the battery when we're storing it. So for example, if we bought 1 megawatt hour at $63 per megawatt hour, that would cost us $63, but we're only storing 0.9 megawatt hours, even though we bought 1.0 megawatt hours. So the cost per megawatt hour of what we're storing is $70, even though the price is $63. Okay, the way it works, you saw in our data that we've got decisions are made every 5 minutes. And so if we're selling at 72 megawatts for 5 minutes, this is the same as selling 6 megawatt hours, because it's 72 megawatts for 5/60ths of an hour. So basically divide by 12, and that's 6 megawatt hours. So now that's our pseudocode for our function, and then the function itself is actually shorter than the description of what it does. First of all, we look at the regional price, and we check if it's above the break price. If it's above, then we can sell, but we have to check how much we can sell. So we have to make sure that we're selling at up to the limit, and we have to also make sure that we can't sell more than is actually stored in the battery. So we calculate those two numbers and divide by, and take the minimum. We're going to use a sign convention of when we're selling it's a negative megawatts, and if we're buying then it's positive megawatts. So the level is going to be the number of megawatts divided by 12, because we're only doing it for 5 minutes. And so the level will increase. Megawatts is negative, so by adding in a negative number, we're decreasing the level when we're selling. When we're buying, we have to do this trick with the efficiency. So we have to compare the RRP, which is $63, with the break price times the efficiency, because it has to be less than that to make it profitable for us to sell. So once again, if it is profitable to sell, then we'll make sure we don't exceed the limit, and we'll make sure that when we're buying, and we'll make sure that we don't buy too much that it overfills the battery. So we compare the current level with the capacity, multiply by 12 because of the 5 minutes, and divide by the efficiency for how much comes from the grid, for corresponding to how much we're going to put into the battery. So in that case, we've taken the minimum of those, and we're buying, it's going to be a positive number because we're buying, so we add that into the megawatt hours level, and that will give us our current level in the battery. If the price is between those two prices, then we don't do anything. So megawatts is 0, and then we can, the megawatts coming to or from the grid, we multiply by the RRP, divide by 12 because it's only 5 minutes, and we add that into our variable that's accumulating our profit, and then we return the megawatts. So we've just defined that, so I'll shift enter to define that class. And now we'll test it. We'll create a battery with 129 megawatt hours, 100 megawatt limit, efficiency of 0.9, and an RRP rate of 70. We'll have a look at what the current level and the current profit is for the battery, and they're both 0, which is what we expect, because we haven't done anything to it. So let's give it some test data. We'll say the RRP is $50 for 3 5-minute periods, and then it changes to $90 and we'll see what happens. So if we run that, and you can see in each one of these lines I'm calling MW decision, which is returning the number of megawatts that is going to be bought or sold, and it actually makes that transaction on the battery so that it will accumulate the megawatt hours level and the profit. So if I run that, at $50, that's a low price. It's below 70. It's below 70 times 0.9. So it's below 63. So therefore we want to buy. We're going to buy 100 megawatts. The battery's empty, so we'll just buy it at the full rate. Over 5 minutes, that'll be 90 megawatts going into the battery to be stored because of the efficiency. Divide by 12 gets us 7.5 megawatt hours, and we've had to pay $416 for that. So our profit is going down as we're buying, and then when it becomes $90, we can start to sell that. Once again, we sell it at the maximum rate. Our level goes down because we've sold, and we've made $750 from that sale, so our net profit so far is minus $500. Okay, let me know if you've got any questions on any of this. I am going through quite quickly, but we'll get to the point where we can start to run our own optimizations on this. So if there's any line in any of the code that you don't understand, please ask, and we can look at it in more detail. Okay, so now we're going to test the battery for a month using a price break of 65 dollars per megawatt hour. So it's an RRP break to 65. Create. So to create an instance of a class, we have the class name, which is battery, and then brackets, parentheses, and all of this data, these parameters will get passed to the init function to create the class. Then create the object. So then the object gets stored in a variable, which we call battery with a lower b. So it's conventional to give your class names title case. So the first character will be a capital, and any word in it will be capital. And then variables that are of that type are going to be all under lowercase with separated by underscores for each word. And so we're just using battery with a lowercase b. We're going to loop through our data frame, which we got from Nemlog. So that's got all the prices in it. And so what would be good actually is if people have got their own notebooks, is to change the dates. I've done January, so if you could choose other dates to get data, and then we can just see if the how things apply in different months of the year. So choose a different months for your data. We're going to loop through each row in the data frame. We're going to call a decision on whether we're going to buy or sell. So if it's less than 0, then we're selling. So we're going to create a column in the data frame for buying and a column for selling. I'm just using the tuple way of assigning values, where we can assign 2 values into one line. So none goes into buy, and the RRP goes into sell. And the reason I'm doing this, we don't need to for the calculation, but the reason we're doing it is just so we can plot a pretty graph. So we're going to plot a red dot whenever we sell, and a green dot whenever we buy. And so by putting this data into the data frame, it makes it possible to do that. Then if we're buying, then we store the RRP into the buy. And if we're doing nothing, then we just store none in both buy and sell. We're also going to store the profit for each line, and we're going to store what the current battery level is for each line. And then, so that's all happening in the loop. Once we're out of the loop, we're going to just print out what our breakpoint was, which was 65, and how much profit we made from doing that. And we'll have a look at the data frame just to see what that looks like. So I'll run that. So using a breakpoint of $65, we made a profit of $535,000 for the month of January 2020. So you might have to choose 2019 if you're doing other months. And you can see the prices here were $50.81, so that was less than 65, so we went in the buy column, and the sell column, we didn't put anything in there. And that shows our profit, so it's costing us money to buy, and that's the amount for each 5-minute period that it cost us. So let's plot these results. So let's look at that. A bit smaller. That fits. Okay, so if we look at this, you can see the red dots here. That's when we're selling. And these green dots, there's a couple of green dots right at the beginning, that's when we're buying. So when we're buying, you see the battery level shoots up to full capacity, and then it stays at full for quite a while until we get to these red dots, and then the battery level drops because we've sold 100 megawatt at 100 megawatts, so it drops pretty quickly to empty. And that's just showing all the buys and sells that happen during the month, and we get a profit of $535,000. So I'd be interested if anyone else runs this for a different month. Let me know what month you ran it for and what profit you made. If you want to run it for a different month, just go up to the beginning. So this cell here. So it's this URL that's important. Just change the dates in there. So I've got to the 1st of January 2020 to the 31st of January 2020. And I put the same numbers in my file so that I know what's stored in the file. So just change the numbers there and run this, and you should get a different month. So put in the chat which month you're going to choose so that other people can choose a different month. So by running that code, you should get a file turning up in your files list. Good. So Peter got 96,727 profit for February. That seems a lot less. I got 535,000 for January, but January prices I think are higher. So I'll try doing February. So yep, first 605. I've definitely got some data there. Let's just see if the profile looks a little bit different. Starting to get this sort of look, which they predict is going to be what the energy prices are going to look like more when you get a lot more solar energy coming in. So it's peaking up until the time the solar starts, and then it starts dropping away. Okay. There you go, 96,727. Well done, Peter. Vince got 123,000 for December. So clearly, January was a good month for making money. So I might go back to the January figures because it does illustrate some interesting stuff that may or may not be shown in these other months. Anyway, it's fine. Okay, so we can see one of the problems that is happening is that when we sell when the price gets just above our break price, and we quickly empty our battery, and then we get these really good price spikes later on. We're not able to take advantage of them. So we'll just bear that in mind for later of how we're going to deal with that. Okay, so we'll come on to demo 3. We're going to try to find the optimum price breakpoint using scipy scipy.optimize.minimize. And what we have to do is we have to create a function which is a loss or objective function, which is what needs to be minimized. So we've already got a function called cost for car fuel, which is really, that's what we want to minimize. We want to minimize the cost. But we have to provide a function that that takes a parameter called x, which is a list or a NumPy array of the values that are going to be passed into the function. And the function that we've got, cost for car fuel, is currently using a parameter called price break. So we'll just create a new function here called cost for car fuel, called loss for price break, that takes this array or list x and takes the first element of that list and passes it into the price break parameter and returns the value of the cost, because that's what we in fact want to minimize. So we can now call minimize, and if you remember, we had that, we've imported that from scipy.optimize right at the beginning. We pass in the function, which is loss for price break, and we don't put the parentheses here. If you put the parentheses here, it actually calls the function. We don't want to call the function before, we want minimize to call the function. It's not us calling the function, it's minimize calling the function. So we just provide its name without the parentheses. Now minimize wants to have this array called x0 that it's supposed to be a NumPy array. You can just provide a list, so I could have just provided a list, and it's the starting values for its optimization. Now if you look up the documentation on minimize, there's got many different algorithms it can use, depending on what data you've got available, determines which one you're going to choose. So we've chosen Nelda-Mead. It uses a simplex algorithm, and just using their description. This algorithm is robust in many applications. However, if numerical computation of derivative can be trusted, other algorithms using the first and or second derivatives information might be preferred for their better performance in general. Our function is not one we can take a derivative of, so it's just got to, we can't get any performance improvements there, so we'll just stick with Nelda-Mead. And we provide these extra things. So display true is just going to print convergence messages. The tolerance that we want for the x values is the absolute error in x opt between iterations is acceptable for convergence, and the f tolerance is the absolute error in the value of the function between iterations that's acceptable for convergence. So let's run this and see what it does. And we're doing this on our car demo, and we're starting with $1.40, which remember we did before, and it cost us $1,100 for me, but you've got different data, so it'll be different for you. So what it does, what minimize does, is it calls our function, and in our function I've put this print statement so we can see every time it gets called. And it got called with a value of $1.40, which was our initial value here, and it worked out the total cost to fill the car was $1,148.76. So it goes, well, what if we use a price break point of $1.47? And it goes, $1,060. It goes, actually, that's better than $1.40. So, you know, we're probably going in the right direction. So then it guessed $1.54. So it's just guessing and calculating. But that put the price up a bit. So going, oh, well, that's worse than the $1.47. So it's probably somewhere in between. So it's gone for $1.50.50. And I go, oh, that's looking pretty good. And so it just keeps comparing and working out which way it's going to go until it gets the value down to $1,040. if we use the price break point of 150. And so if we look at the graph now, when we've got $1.50, we can see that using that price point, we never run out of fuel, which is pretty much what we want to do. We want to buy as cheaply as we can, but we don't want to run out of fuel, because as soon as we run out of fuel, we get hit with a big penalty. So now, you guys have got your own data sets, random data sets. So try running that optimization and seeing what you're getting as the optimum price point for when you should buy fuel. Show the code for anyone who's typing it in. Alright, so Peter got an optimum price of $1.50.5. That's pretty close to my optimum. So he saved about $140 by doing that, which is pretty close. I saved $108. So if anyone's having any trouble running this, just remember to ask questions in the chat and I can try to help. Vince got $1.48.3. So Vince, how much money did you save with that price? Okay, so I hope you went through all the lines of as it's going through the optimization and saw how it's picking the next number, and if that made sense to you. And now we can look at challenge 3, which is to do the same thing for our South Australian, our battery, our Tesla battery, using Queensland prices. So what do you need to do to be able to use scipy optimize? So this is the class challenge number 3. Yeah, so that optimization, to do that manually is quite laborious. You run the function and then think of the next number you're going to choose, and then try that, and then and do it over and over and over again, and just not be confident that you might have covered the whole range. So it's quite good to have an optimization function that you can just call it and it can go and do. And even if you've got something that takes a long time to run, you can run it overnight and come back the next day and see what the result of the optimization was. Okay, so for challenge 3, remember that we've already done a lot of the work. So here's all the code where we did the testing the battery for a month using a price break of $65. So we could put that into a loss function that's going to be the function that we're going to minimize. And it's going to be based on this RRP break. So that's going to be the parameter that comes in. But remember to use it with scipy minimize. It's a good idea to take it as the first element in the list. Okay. Elaine has asked, is it possible that the optimized breakpoint could be lower than $1.40? And that's definitely true. $1.40 as your guess point doesn't have to be the lowest number you want. It can be in the middle somewhere, and it will try either side. In this case, it got such good results from going higher that it didn't even bother to look lower. But if you started at $1.60, it would then try lower and higher, and should eventually come to the same answer. So $1.40 just has to be a guess that's going to be close. So try it again using $1.60 as your start point. I'll give it a go here for me. So it's traded $1.68, it's traded $1.52, $1.44, and it's finished on the same number. Does anyone want more time to try to work out this loss function for and how to optimize the battery? So I'll show you what I'll do. I'd take all this code that we wrote before, and we'll just copy and paste that down into challenge 3. But we want to indent it because we're going to put it into a function. So I just select it all, press tab. We were collated using 2 space tabs, and I'm used to using 4 space, so I've got to get all of them as 2 space. Okay, so it's find a function, we'll call it loss function for RRP break. So the requirements of this loss function for minimize, it's got to take a parameter called x, which is going to be a list, and the first element in the list is going to be the RP break that we want to use. So we're going to create a battery. We're then going to put data into the data frame so that we can do our plot. We don't actually need to do that, but it's really useful to have a look at the plot afterwards to see how things go. And we're going to say the profit for each by itself is this much, and that's going to be the profit. Now this profit here doesn't include any benefit of having storage in the battery at the end of the time period that you're looking at. So we'll run it using that for the moment, and then we'll just look at if we can improve our profit. So a loss is the same as a negative profit. So we'll just take the negative of our profit. So it's battery.AUD profit. and that's what we're going to return. Now, and then so we'll just define that function. I'll press Shift Enter. Then we're going to call it using maximise. That's the name of the function. So last time we were looking at the car one. This time we're going to look at the RRP rate. This function we just created. We're going to start off at $50 per megawatt hour. We'll use the same method. We want $50. We want the price to be within 0.1, but the profit for the month, we'll say that within $10. That's fine. We'll print the result and then we'll plot the battery. So let's run that and see how we go. There we go. So 539,000. With our first guess before of $65, we got 535,000. So that was we were guessing pretty close to the answer. And you can see that if we started down at 50, it was only 383,000. So we've improved quite a lot from $50 to $62 as our price breakpoint. And when we look at the results, you'll see we're still doing lots of buying and selling on the battery. In fact, it should look pretty similar because we were quite close before. So, for people who are using different months, I'll be interested to know what you got as your optimum price break point. Okay, Vince got 59.66. Well, that's good. It's not too far different from 62.18 because it's all very well to optimize this for the current month, or for a past month, but the new months are going to be different. So we've only got past data to be able to optimize for the future. So it's good that we're reasonably close. So I got 62.18. Vince got 59.66. So one of the problems with our formula for calculating profit is that we're not putting any value for any storage that's left in the battery at the end of the month. So basically we're favouring any price that makes sure that we sell everything at the end of the month. So we can put in an additional, let's see, we can just copy and paste. When we define our loss function, we were using a battery.aud profit, but that's the profit excluding any storage value. So if we include the storage value, then we basically anything that's in the battery at the end of the month, we're going to sell at least RRP rate. So if we give it a value of that, then that will not penalise any scenarios where any of the prices which end up with a level at the end of the month. So let's return the profit including storage and see if that changes. It may not, but let's see. I'll define that as our new loss function, and then we'll run that one. So in our case, it came out the same because it was the profit excluding storage is the same as the profit including the storage. But if you look at some of the previous data when it was doing calculations, so here if the price is 62.50, we had a profit including storage at 538, but actually there was some energy left in the battery that we could sell, and that would give us a profit of 539,151. So for this month we're looking at, we'll probably find that the prices were really good at the end of the month, which is why most of the ones here we're going to sell anyway. But for other months it might be low prices at the end, in which case you really do want to give it a profit, give credit for that value that's stored in the battery. Peter's got a optimised price of $66.28 for February. So it's good, they're all around the same ballpark. Okay, challenge 4. We want to modify our decision. Okay, so if we look at the charts, we can see that as soon as the price gets high enough, we just sell everything that's in the battery. Which means here we were selling everything that's in the battery until the battery was empty. So the battery's empty here, and then we got this big price spike. So we weren't actually able to sell anything because we had an empty battery. And similarly here, we probably got some of the early price spike, but these later price spikes we didn't get. So we have to, we've optimized it for our current logic, but maybe we can change the logic to improve how much money we can make from running this battery. So the idea in challenge 4 is to modify the decision-making function so that if the regional price is only just higher than the RRP, only a little bit of electricity is sold, but if the RRP is a lot higher, then it is sold at the maximum rate. And similarly, if it's a lot lower, we want to buy a lot, but if it's only just a bit lower, we'll just buy a little bit. So we've got to try to work out how to put this Python, sorry, I'll put it on the screen, how to put this Python logic, put this logic into Python. So in the chat, people come up with some ideas of how to do it. And the answers I've put my idea, but there could be other ways that could be even better. All right, Peter says he's going to ask me, so that's good. So there's probably some different things that you could do. You could decide that if it's close, just don't buy or sell at all, and just wait for those big spikes and try to take advantage of them. I did one where I thought maybe the 100 megawatt limit was too high, and maybe if we dropped the limit down to say 50 megawatts, then I wouldn't have my battery discharging so quickly, and I'd still have some left in the battery to sell when the price spiked. But I found that it actually reduced the profit when I did that. So obviously it likes to be able to buy and sell lots of times in those situations. But when it's and when you get those price spikes, it wants to be able to sell or buy at those at the full rate that it can. All right, so how many people want to have a go at this challenge? It's a fairly advanced one, so I can give you time, or if you're all giving up, I can just walk you through it. Okay, so Vince has gone for an inverse staggered approach of 20% increments. So does that mean that you want to limit the amount of battery that you can charge or discharge to 20% at a time? Or okay, so Peter's saying he's giving up. We'll just see a bit more of what Vince is saying. So Vince, you're looking at the code for charting. So where we set DF at index buy and DF at index sell, that really is just for charting. It doesn't affect the decision-making process at all. All the decision-making process happens in the class, the battery class. So it's in, let's have a look at the battery class. So here's our battery class, and here's our decision function. So this is the logic of when to buy or sell. And it's currently, if the price is higher than our break price, we just sell at our maximum rate. And if the price is less than the break price, then we buy at the maximum rate. So we're setting these challenges during the session because you actually learn more when you're doing the challenge than just watching someone else do it. So I'm trying to, like when I do them for you, I try to show you the steps that I'm going through, how I would think about setting it up. But until you actually have to do it yourself, you don't understand those nuances in the code that and why they're there. All right, yeah, so Vince is saying 20% slave, so it's not depleted completely. Yep, that was my original way of doing it, and I ran it. We can run that quite quickly, actually. Let's try running that. All we have to do is change the our megawatt limit. So rather than 100, we could just do 20 as our limit and see what it looks like. So this is for $65. And look at that, the profit's gone down from 535 to 236,000. So we've almost halved our profit. It's just amazing. So you can see these lines are less vertical now. It's hard to see with so much data on this chart if you did it, but yeah, they've got more of a slope in them now because we've reduced the limit down to 20 megawatts rather than 100 megawatts. So surprisingly, that's not the answer. So there it is with 100 megawatts, and we get 535 and very steep lines. Okay, I'll walk through how I would do this. So I've got the answer down here actually. So this is our battery class. Now I've added in an extra parameter here, RRP factor equals 1. So that's basically saying how much we want to buy if the price of the RRP is twice our break point, or sorry, half our break point, and how much we want to sell if it's twice the break point. So in our decision, I've got rid of all the comments here, but so this is what our old decision was. It was just we had to go less than our limit, and we had to go less than how much was left in the battery when we were selling. So those are still limits. So we've got, I'll put them the other way around, but we've got our maximum discharge rate and how much is left in the battery. But I've also put a limit in now, another limit. So now there's 3 values we're comparing. And we look at the RRP, we see how much higher it is than the break and divide it by the break price. So we get a percentage. And then we multiply that by how much we're going to sell should the price be twice. Now if you look at the price data, you could see it was mostly between $50 and $140 per megawatt hour. But if you look in some 5-minute periods, it can be up to $14,000 per megawatt hour. So if you can sell during those times, you can make a lot of money. So this is what we're going to do. We're going to multiply it by this factor, and similarly when we're buying, we'll have a factor. We'll look at what the percentage is of how far the price is from the break price. So that's what that calculates, and then we multiply that percentage by our factor for how much we're going to buy. Yeah, if we wanted to be more complex, we could add different factors for buying and selling, but we'll just use the same factor for now. And that's really the only thing. So we just have to store the factor and put in these third values in here. So I'll shift enter on that to define our class for the battery. Now when we define our loss function, we're now trying to optimize on 2 values. We've got to optimize on the break price, and we've got to optimize on the factor. And we can actually have many values that we're trying to optimize. And this is where the optimize really comes into its itself, because trying to keep track of this manually is almost impossible. So X is going to be a list of parameters. The first one is going to go to the break, and the second one is going to go to the factor. Then we're going to create a battery with those characteristics. Then we're going to run it through all the month's data. We'll work on including storage in our profit calculation, and our loss function has to return the negative profit because we want to minimize. There's no maximize function, but maximize is just minimizing the negative of the number. So we'll do that, and then we can plot the result. Okay. So we've defined the battery, now we'll define the loss function, and now we'll run it. Oh, and so here's the starting values. I've put in the starting value of 10 and the starting value of 62. So $62 was pretty close to our starting value before for the best breakpoint for the price. And our factor was like a really high number. We were just saying buy and sell as much as you can. But now we put these lower numbers in, and we can see, look at the profit. Before we were 535,000. Now we're at 825,000. And it's trying different values of breakpoint and factor. Okay. Just scroll down. There we go. So it's decided these spikes are so good that we'll buy and sell during the spikes and ignore the rest of the time. And we've increased our profit by 50% by doing that. So we just fill the battery and then just wait for the price spikes. And that's what it's come up with. It's come up with a breakpoint of $90.25 and a factor of 27 megawatts. So let's keep a note of that. So that was with a start point of $62.10. It became our optimum of $62.10. We've got a breakpoint of 90.25 and a factor of 27.1534 megawatts, and it gave us a profit, including storage, of $825,000. So now let's run the same thing using 62 and 50 as our starting point. So you can see it's coming to actually to a different solution. Looks similar. It's actually going much lower when it's doing its sales. But the profit that we got, 754,000. So that was starting with 62.50. So this is what you have to be careful of when you're running these optimizations, is that it can come up with a local minimum. And so the 750,000, so that 754,000, that's the local maximum of profit. and so it didn't see that if it increased the price quite a lot more to 90.25 and used this much lower factor, that it would get an even higher profit of 825,686. Yeah, so that's a couple of different scenarios, but it's much easier to just try a few different starting values than to try to manually guess lots of different combinations of breakpoint and factor to come up with the solution. So try running that through on yours. It might even be worth trying to optimize this profit excluding storage rather than the profit including storage, and because the including storage one actually favors the higher RRP breakpoint, because we actually multiply that by the level in the battery to give us a value for profit. So yeah, give those a go, see if you can come up with any what your optimum values are for price and factor. So that's the end of my session for now, but I'll stay listening to Slack, and I can answer any questions on that for another 5 minutes. But I hope you enjoyed tonight's presentation.